So what will eventually come down to is a process, is a step-by-step process to define what we're going to call orthogonal vectors or orthonormal basis and stuff like that. So it's something that we're going to build up to. So for today, we're going to just have a whole bunch of definitions and a bunch of theorems that we're going to throw up there, give examples of, and try to do some quick examples of, and then we'll get to that main point on Wednesday, and that's how we'll end our class.
Does that include one question from staff?
Yeah. I hope it's just one. I think it's just one. Yeah. All right. So let's start off with the definition. All the stuff is happening in Rn or is defined in Rn, but this could be, for our sake, R2 and R3 would be our limit for exam type questions. But it becomes more interesting beyond that because we're finding, orthogonal vectors. It's easy to visualize in 3 dimensions, but we'll take it in higher dimensions, or it can be taken to higher dimensions. So let's see, a set of vectors v1, v2 through vn in Rn is called an orthogonal set of all pairs of distinct vectors in the set are orthogonal. If, this is an if. I was thinking that sentence didn't make sense. If all pairs of distinct vectors in the set are orthogonal. So that is, if we take any 2 vectors, we dot them, we get the dot product to equal to 0. And if we took 2 of the same vectors and dot it, or we took a vector and dot it with itself, we're obviously not going to get 0, right? Because a dot product, remember the definition of a dot product is something about the magnitude or length or something like that. So we want this for different values of I and j. So we can jump to a quick example from the homework set. Let's just do one, maybe 2 of them. And if we're dealing with something in R3 in this case, or in these 2 cases, we want to make sure we dot all the possible combinations. And we talked about combinations, I think. How many possible combinations do we have? So we dot these 2. Let's call this maybe U, V, and W, or V1, V2, V3. I'll just call it U, V, and W. So we want U dot V. Remember the dot product gives you a scalar, so we should get a number out of this. -6. Better write this down. +4 plus 2. That's equal to 0. So U dot V is 0. U dot W. If we take a look at that, that's -3, -1, +2, or +4. So that's also equal to 0, so that checks out. And then V dot W would be these 2 vectors. That would be a 2 minus 4 plus 2, which is also equal to 0. Now, technically, you should check W dot V, but fortunately, the dot product is commutative, so all those can be taken care of. So in this case, we only have 3 things to look at. So they're all equal to 0, so yes, this is an orthogonal set. We're just taking the dot products of these things, yeah. If it's a huge set, then you still need to take all the possible combinations of a huge set.
Would you use like
You could, yeah. And then we could do the same thing for this one. I wanted to do an example where it's not orthogonal set, but it probably is. Let's try it. Again, we'll use u, v, and w. Those are easy vectors to remember. U dot v is 4 plus 0 minus 4. That's equal to 0. So that checks out. U dot w is negative 8 plus 5 minus 2. Nope, plus 10 minus 2. So that's also equal to 0. And v dot w is negative 2 plus 0 plus 2. Yeah, if it equal to anything else aside from 0, then you just stop wherever that happened and just say this set is not orthogonal.
That's plus
Where? That's plus 10. This is orthogonal. And if you just imagine this orthogonal set, it's in 3 dimensions, if you just imagine how this looks like, there'll just be 3 vectors in 3D that are perpendicular, they're all mutually perpendicular to each other. So if you have these 3 vectors in 3 dimensions that are all perpendicular to each other, what can you say about that set? They form a basis for all of R3, in this case in R3, yeah, they form a basis. So they span R3 and they actually do form a basis because they're all linearly independent of each other, right?
So an orthogonal set basis for...
Well, in this case, if you have 3 vectors in 3D, then they're going to span all of everything, and it's a basis.
Can we generalize that to the R and...
Yeah, so if we have n vectors that are orthogonal, then that's actually a theorem that's going to come up. I'm kind of thinking ahead a little. I was going to try to visualize this, but is it worth visualizing?
It's pretty basic as far as
Yeah.
spaces go, though, right? Like, it's what it means to be in a 2-dimensional area is that there can only be 2 orthogonal.
2 orthogonal vectors, right. All right, so let's take a look at some theorems here. This is something that was kind of mentioned already, and we said that they're linearly independent. And then the next is a definition. Sorry. Let's try it again. So these 2 ideas we've kind of just discussed in the last minute and a half. If you have an orthogonal set of vectors, then because they're all perpendicular to each other, they're going to have to be linearly independent. And that kind of made sense, right? And then if you take here, an orthogonal basis is a basis that's orthogonal set. Now, let's make a couple of comments here. If the orthogonal basis has n vectors, and the n matches with the Rn, then it actually forms a basis for all of our n. And we know that Rn itself is a subspace of Rn, so we can just replace W with Rn, and that makes sense. That's okay. But this definition of orthogonal basis doesn't have to complete all of Rn. It could be a subspace, a proper subspace, which means not the whole thing. If we're in R3 and we only have two vectors that are orthogonal to each other, that would form a basis for a subspace, but then there's another, that would be a plane. So, and let's take our example from the previous page, and let's just take 2 out of 3 vectors. So suppose let's take this one because it has a 0. 4, -2, or 4, 2, -2, and 102. So 4, -2, 2, and 102 is an orthogonal right. Thank you. So suppose this is an orthogonal basis for W, then W is a subspace, and that subspace is a plane, right? So we know that this is orthogonal from the last page, from the previous page. Let's just call it U and V. And since they're orthogonal and they span a plane, which is a subspace, a proper subspace in 3 dimensions, then we can say that this is an orthogonal basis. And just for a little bit of a review, since we're getting close to the final exam, how would we represent this plane, or what is one good way a quick way to represent this plane? So if we just say, take each of those vectors and have a parameter like t and s, so t times 4, 2, -2, plus s times 1, 0, 2, that can be your plane. And then if you want to, we don't ever have to make an ax plus by plus cz is equal to d equation of the plane. But in case you were asked that, you would need to use some cross product information from.
Can we do that? Just as a
It's Calc 3, so.
but like just
Nah. Well, we're kind of rushing, so we'll do this another time. For this class, you never really had to learn cross product, correct?
But you will in Calc 3?
You will in Calc 3, and you will in physics and stuff like that. So it's an important concept in those classes. Okay. So that's an orthogonal basis. Let's move on and see what other theorems are around.
Will you actually learn it, or will they say this is something you should have learned in linear algebra?
No, it's not something. So officially, the cross product does not fall under linear algebra. It's not one of the concepts in linear algebra.
Oh, that's why it was in that. So
Yeah, so it's just an added bonus if you learned it in linear algebra, which you did, right? I did talk about it.
I read it.
So you guys got your bonus already.
Then
So.
again, the approach I did to handling a 3x3 matrix and multiplying is relative to cross product.
Like the cross product
Except
way.
without the IJ3.
It actually is backwards. The cross product is the determinant of that. Well, never mind.
Okay.
Okay.
Seems like.
All right. Let's move on and keep looking at some of the theorems and definitions that are included in this section. Now we have a set, a smaller set. Now k can be equal to n or it can be less than n, but k is going to be just the number to represent that this is possibly less than the n, the dimension of Rn. So suppose V1 through Vk are orthogonal, is an orthogonal basis for a subspace of W, and let W be any vector in W. Then there is a unique scalar C1 through Ck such that you can write W as a linear combination of that orthogonal set. And not only does there exist these constants, these scalars, but there actually is a formula to find those scalars. And that formula is given by Ci is equal to this. It's a dot product divided by this. Does this look familiar? It looks like a projection. Yeah. So this is kind of like a projection. A little bit different because there's some, we played around with times the unit vector thing business. But this is a scalar. All right, let me attempt to give a visual for this. And for the idea of giving a visual, let's stay in 2 dimensions. Actually, I think we should probably go into 3 dimensions. Let me change everything here. So let's say we have V1 and V2. To represent a subspace. And remember that subspace, if I span 2 vectors in 3D, my subspace is a plane. So let's say I have a plane that represents, and the V1 and V2 are on that plane, so that's my subspace. So this is my W, and I got V1 and V2 in there in R3. Now what they're saying is that if I have a vector W that's in W, so let's say this is my vector W that's on the plane, then I can find a linear combination. W is equal to something with a V1 plus something with a V2. Right? So what are those somethings? No, well, those somethings are just scalars. But how are we going to find those scalars? Now, let's take a look at how you're going to find V1. To find V1, what you're going to do is you're going to basically stretch V1 out and project this down. Oh, I need V1 and V2 to be orthogonal, which means they have to be 90 degrees perpendicular. So let me change my V, sorry.
Just say that it's tilted.
Yeah.
It's tilted, okay, thank you.
You can't really tell.
Yeah.
Yep,
Just say it's on the XY.
yeah, or not exactly XY, but it's tilted in a way that this is actually, so So what we need to do is, it is exactly the projection. It's a scalar projection of W onto V1. And so given that this is perpendicular over here, project it down, this length over here is a scalar projection. Which is W dotted with the base that you're projecting on, divided by, I think we called it the magnitude of V quantity squared, which is the same thing as a dot product. So the scalar projection, W dotted with V1 over the magnitude of V1 squared, but the magnitude of V1 is the same thing as the dot product of V1 with itself. So that's how the formula is related. So that's how you would find C1. And it's a scalar, right? And so you would find C2 similarly by projecting W onto V2. And so when you project W onto V2, you're going to get C2. Okay? Is that okay? Dotted. Divided by, or V2 dotted with V2, and then that's what you would get. And so I mean, it should make sense. That's a definition of subspace, that if you have any vector in W, it's in the span of those vectors, or another way of saying it, the span of something means it's a linear combination.
But can't you just find them both by solving the system for C1 and C2? So that you can
You can do that too, but we're trying to establish the types of formulas that we'll need here, which is really just projection formulas.
The length squared.
Yeah, that was our formula for scalar projection, but note that the length squared, V1 squared, is the same thing as a dot product.
You left it out of your description of what
Oh.
C2 is.
Yes, thank you. This is, you're looking for this, right, Justin?
Kind of, yeah, no, I guess I wasn't sure of the connection between that.
Yeah, that's all right. So this really falls on some sort of a projection exercise. Good? All right, move on. Moving on. Oh, there's examples here. I suppose we should do one. We might as well.
I don't remember how to do projection.
All right, we'll remember now. So we could do one, let's do number 7 and maybe number 9. Show that the given vectors form an orthogonal basis for R2, then use theorem 5.2 to express W as a linear combination of these basis vectors. Give the coordinate, what? Give the coordinate vector WB with respect to, yeah, it's just, okay. I didn't mention that, but we'll write it that way. So let's take a look at number 7 and really beat this to death. V1. First, we want to make sure that it's orthogonal. So there's only 2 of them. Let's dot them, and then we'll see that this equals 0. This is 4 minus 2 times 2 is 4, so that's equal to 0. So this is an orthogonal set. Next, we want to express W as a linear combination of V1 and V2. So as Becca said, we can solve for this by letting this equal to C1 and C2 and doing a system of linear equations. But we have now advanced to something a little fancier, and that is to use the projection idea. And so we'll take W, which is 1, 3. We're going to dot it with V1, which is 4, negative 2. And we're going to find V1 dotted V1. And then that number is going to go as a coefficient. So let's see, the dot product is 4 minus 4 plus 6 is 10. And then 16 plus 4 is 20. So this is 1/2. So that's our first coefficient. Next coefficient down here is, I'm just going to write down the symbols W dot V2 over V2 dot V2. And W dot V2, I'm going to take my W and look at my V2. So 1 minus 6 is negative 5. And then V2 dotted with itself is 1 plus 4 is 5. So that looks like it's negative 1. Okay, now this last bit that they're asking for is give a coordinate vector W, which is equal to 1, negative 3, equal to another vector, or essentially the same vector, but with respect to this basis, B, where B is equal to this V1, V2 business. What this is saying is that now I'm going to write this not as 1 comma 3, but I'm going to write this as 1/2 comma negative 1, and that's going to be my new components if I want to write my vector with respect to this other basis. Say it again? No. This isn't a scalar multiple or anything. This is the same vector W, and I don't know if I should write it like this, where I say 1, negative 3 is equal to 1/2 1 sub B. But what I really wanted to write is, maybe if I write it like this, W can be expressed as 1/2 comma negative 1 in a different basis. So what this is saying, in 2 dimensions, it's a little easier to draw.
Also, if you have the same vector and you move the basis over, then that's...
Not move it. The basis technically doesn't move around.
Sure.
The basis technically. Here, let me see if I can draw. It's a little bit. You can kind of think of it as a transformation. So what did I just draw here? What is this? Okay, in R2, I have my Chris mentioned the ij business from the cross product, ijk.
Oh, yeah.
So in R2, I have I and j as my two, we call it basis vectors, right? And whenever we write a vector, like we do here, w is equal to 1, -3. W actually comes from 1 times the I vector plus -3 times the j vector. And if you've done a lot of physics, you know that you've written a lot of your vectors this way with ij, ijk. And these numbers over here are significant in that they are the components, or they are the scalars that you stretch your standard basis vectors by to get this vector 1, 3. Now, we have two new vectors, 4, -2. Let's see if I can do this in blue. 1, 2, 3, 4, -2. Wow. And 1, 2. 1, 2. Okay. Now we've proven that this is orthogonal, which, because I drew it to scale, it actually looks orthogonal. But now, what we're saying is that instead of using I and j as my basis vectors, I want to use these two blue vectors as my new basis vectors. So if I have another vector 1, -3, 1, -3, oh,
This is probably going to work better if your first basis vector
what's down?
is 4 minus 2 instead of 4
Yeah.
minus 1.
Well, I guess, wait, before we get to this new vector, what I'm going to do is, you know you know why I did those grids? Because these are my grids for my standard basis. Now, if I have a new set of basis, I'm going to have a new set of grid. And my new set of grid is going to look like this. So but it's not skewed. It's tilted, it's rotated, and it's stretched out. But everything has to be perpendicular still.
So it's sort of, what I'm saying is that the vector is going to be
No, I don't want to say skewed, because skewed makes me think that instead of rectangles here, I have parallelograms, and I don't have parallelograms. They have to be rectangles, which means these have to be perpendicular. They all have to be perpendicular to each other. And so what I've done now is I've switched my basis to be this, and so I would have a rectangular grid that looked like this. And that means if I want to express that point that I had earlier in green, I would take this vector 4, 2 and take half of that vector and take this vector, instead of going up, it'll go down, -1, and I would get to that same place using my grid, using this blue as my new grid, instead of the black where you move 1 and -3. I would move, in the blue, I would move 1/2 and -1.
So 4 and -2 becomes a new 1, 0.
4 and -2 would become your new 1, 0, 0, 1. Yes. Technically, we did this with any two vectors that are linearly independent by making this orthogonal instead of having those parallelograms as your grid, now it just becomes rectangle. And then, jumping ahead, we're going to, instead of rectangles, what we're going to do is we're going to shrink these basis vectors down to have unit length. And so it would really actually look like a grid, the same grid that we had, except it's rotated. Yeah.
Is there any projections to it?
Technically, the projection is this green vector was projected onto this first blue vector, and it was projected onto this other vector backwards. So yes, there was some projection here.
So this might, maybe violate the definition or something. Like, is there some scalar you can multiply both v1 and v2 by to get 1, 0, 0, 1?
Yes.
And then if you multiply that scalar by w, would you get 1/2 -1? For a vector rather than scalar, I don't know.
I
Is
think
it
so.
possible to do that kind
Yeah,
of
I think so. You're just going from our new basis back to our old basis, and then expressing w as that.
I'm just
Yeah.
trying to see a change of basis as a linear transformation. I
Yeah.
guess.
Yeah. Because the change of basis for this, it'll just become a rotation. So I guess a comment to why this might be important. This, if you're didn't I talk about why this is important already? Okay, let's move on. What? Video games. Well, that's just one application of it. Yeah, so video games. What? Rapping? Oh, graphing. I thought you said rapping. All right. So this is something that I had already kind of mentioned. A set of vectors is called orthonormal, not just orthogonal, but orthonormal. If it's orthogonal and all the vectors are of unit length. So this is where it brings it back down to unit length. Orthonormal. An orthonormal basis for a subspace of W is a basis that is an orthonormal set. So an orthonormal set is they're all the vectors are perpendicular to each other, and all the vectors have unit length. And then they would form an orthonormal basis for your subspace. So if we take a look at that example that we were doing, is this an orthonormal set? Or is this an orthonormal basis for R2? So it's not orthonormal. It's orthogonal. We saw from last time that it was actually orthogonal, but it's not orthonormal. Can we make it orthonormal? Just by making both of these vectors as a unit vector. So let's shrink V1, or I don't know, shrink or stretch. Let's adjust V1 so we make it a unit vector, and let's call it U1. Do you remember how to make a vector a unit vector? Divide by its magnitude. So what's its magnitude? This is 16 plus 4 is 20. Square root of 20. So 4 over root 20, negative 2 over root 20. that's my first vector, and if I take my second vector and I do the same thing, 4, is this 4? This is 1, sorry. 1 and 2, so 5, root 5 is the magnitude. So now this is both orthogonal and unit length vectors. The V over V, V over magnitude of V, yeah, to make it a unit vector. So this makes it into a unit vector. Now I have unit vectors and they're perpendicular, so this is an orthonormal set. And since these are two vectors that are perpendicular to each other in R2, it's going to span all of R2. So not only is this an orthonormal set, but this is also an orthonormal basis for W, a subspace of R2. In this case, there's 2, so it's a two-dimensional subspace of R2, which means it's all of R2. Okay? So a theorem here. Suppose we have an orthonormal basis for a subspace, and W is some vector in there. Then W can be written as a linear combination of the orthonormal set. Now, this looks a little bit different from what we saw earlier, but I think it's the same. Do you think it's the same? It is the same. And what's missing and why is it missing?
What do you mean? Like, it looks like the constants are just being expressed as dot products.
Right. But before, the dot products that the constants were representing
Those
were these. What's the difference now between
you're
this?
dividing by the magnitude because it's already been taken care of, right?
What do you mean taken care of?
Like they divided by the magnitude in that one already. Is that what you mean?
Kind of.
Yeah, it is.
That's it is. Sound-
Because they just have the top, the W times the vector, because there's no reason to divide out the magnitude of the vector, because if it's a unit.
That's what I was looking for. So Q1 dotted with Q1, which is what this first one is supposed to be divided by, because Q comes from an orthonormal basis. That means each of these have unit length, and Q dotted with Q is the same thing as the magnitude of Q squared, which, if it has unit length, is equal to 1. Right? So they just said denominator is all 1, so that's what happens.
So why did they even bother putting this in there? Kind of dumb.
Yeah, maybe they should have just jumped to the orthonormal set from the beginning. But they wanted to take it orthogonal first, and then now let's make the vectors all unit length, and then now it's orthonormal. Yeah.
I don't get the last part of that stuff.
The representation is unique?
Is it is, not it?
Is. Oh, is, yes. Oh, typos. That's a typos that spell check doesn't catch, right? Wait, where's my first typo? First typo was... Is it? pairs. Is it this one? Pairs.
Set of,
If all pairs of this thing. What?
It's the after the word set.
Set. If. And then this one was a typo.
You also
Is.
have one for an orthonormal basis.
This one?
The second bolded orthonormal basis.
It doesn't matter because it's just a single. It's singular. An orthonormal basis. Yeah. Thank you. All right. Should we do some examples? You guys got the idea? You guys got the idea. Let's move on. Oh, okay. So now let's turn to how these vectors relate to matrices. After all, we have been talking about matrices, right? So they must be important. All right, first theorem. If you have a set of vectors that are orthonormal and you put them in a matrix, then the columns of an m by n matrix form an orthonormal set if and only if that's equal to that. The transpose of Q times Q is equal to the identity matrix. Is that better? Okay. It's not like I'm just doing a recording. I'm just reading it. Okay. So the simple example that we had, we're just going to go one way. We're not going to prove this. We're just going to show that it actually works at least one way. And so the one way that we're going to go is, I think that we're going to go, I don't know which way we're going to go. Oh, whatever. The example that we had in the previous page where U1 was equal to, what is it? Do we want to reduce that? Does this reduce, or if you rationalize or whatever? I'll just leave it. 4 root 20. What is it? I'm just going to keep 4 root 20. Negative 2 root 20. And U2 is going to equal, what was it? 1 or 2? 1 over root 5 and 2 over root 5. We could. All right. What is it? 2 root 5? And negative 1 over root 5. They just simplified for doing that rationalize or not rationalize. Something to do with simplifying in algebra. So let's double check. We know that this is an orthonormal set, right? So let's let Q equal, and let's make this into our column vectors. 2 root 5, or 2 over root 5, negative 1 over root 5, and then 1 over root 5, and 2 over root 5. So what they're saying here is that if we have an orthonormal set that make up the column vectors make up the matrix, then if we multiply this with its transpose, or multiply the transpose with this in that order, we should get the identity. Of course, if it's the identity, we should be able to switch also. So the transpose is what? 2 over root 5. we switch, instead of reading across, we would read down, negative 1 over root 5, positive 1 over root 5, and 2 over root 5.
Can we just like pull out root 5 and just make things easier?
When we multiply it, before we can't pull it out before we multiply it,
You can't?
because if we do that, then it's not orthonormal anymore. It'll be orthogonal. So we want it to be orthonormal.
But won't it just not affect the multiplication?
It probably would. Instead of the identity, you'll get a constant times the identity.
So then we can just put it back in.
You can, yeah.
Constant would be 1 over, would be root 1,
Root
root 5.
5. I think it's root 5 times root 5. So I think it'll be 5
Right.
or 1/5 or something like that.
But it's related to the root.
Yeah, it's related to the denominators here. All right, so let's multiply this out. QT times Q. It's the row times the column. So it's 4 root 5 minus
1? Oh. Wait, what? Why is the root 5? Yeah, isn't it 4 over 5? Is the
That's
root
4/5, huh?
Yeah. 4 over 5.
Oh, 4 over 5. I don't know what I'm doing.
You got to end up with 5 over 5.
Right, we need 1, right? We need 1 out of this.
Right, and you have
So
one
Oh, I see, -1 and
minus 1 is minus 1 and plus. All right. Whew. Thanks. So this is equal to 1. And then the first row in the second column is 2 over 5 minus 2 over 5 is 0. The second row in the first column is 2 over 5 minus 2 over 5, which is also equal to 0. And the second row in the second column is 1/5 plus 4/5. And this is equal to the identity. Okay? So that is what they're trying to say in this particular theorem. And then also, if we happen to know about matrices whose transpose product, wait, don't we know about matrices whose transpose times a product is identity? We did some of that.
they're like reversible.
Let's do another example. Do you remember switching the matrix, the 2 rows in the matrix? I think we called it P. For example, it's the permutation matrices. If we switch the order, and then the PT happens to also be equal to the P inverse. Well, in this case, it's the same. Should I pick something that's not the same?
Invertible. You already know it's invertible.
Yeah. Well, anyways. And then we know that PT times P is equal to identity in this case. That must mean that if we take the column vectors here, that 1, 0, 0, 0, 0, 1, and 0, 1, 0 form an orthonormal basis for the subspace. In this case, it's all of R3.
So
And this had just, in this case, it just happened to be the standard IJK vectors.
So the converse is true.
Yeah, this is an if and only if statement, so it goes both ways.
When you said subspace, you mean R3 is a subspace of like the
Of R3. Well, in this case, since we're in a 3 by 3 matrix, we're looking at subspaces of R3. Because these vectors have 3 components, so we're stuck in R3.
Make it like a space rather than a subspace.
Yeah, well, a space itself is a subspace of that space. So in R3, the subspaces are either the point at 0, 0, a line going through 0, 0, a plane going through 0, 0, 0,
Right.
or all of it.
Oh, okay.
So we want to say all of it is also a subspace. Okay. All right, so that's that theorem. Let's see if we can throw the definition now. Since we are moving towards matrices and orthogonal stuff, we might as well define what an orthogonal matrix is. So here's a definition of an orthogonal matrix. N by N matrix whose columns are an orthonormal set is called an orthogonal matrix. So, it's what?
It's just weird.
Why is it weird?
Because it should be called an orthonormal matrix.
Orthonormal matrix, yeah.
It's got so much history that it can't be consistent. Is that the problem?
Well, because they could either call it orthogonal or orthonormal, because having a set of orthogonal column vectors isn't really going to do anything special to your matrix multiplication. So they had a choice of calling it orthogonal matrix or orthonormal matrix, which is going to be the same thing, and they chose orthogonal because it's easier to say orthogonal. Say orthonormal 5 times. Orthogonal, orthogonal, orthogonal is easy to say. Orthonormal is a little bit trickier. I don't know. I'm just making shit up now. You're right. It's why don't they call it orthonormal? Is because there's not much more to give with orthogonal basis. So that's probably the reason.
No, I'm just curious. Looks like there's more stuff, or is it just? Never mind.
Do you get to figure out what the orthogonal sets matrix is called?
No, we're gonna. We'll get there.
What happens next?
So this theorem is kind of paired up with the other theorem when they say from the theorem 5.4, when they say QT Q is equal to the identity, it's essentially saying that the transpose is the inverse. And so those special matrices whose transpose is the same thing as the inverse is your orthogonal matrices. So we already came up with a couple of examples, right? Example is that permutation matrix that we had, 1, 0, 0, 0, 0, 1, 0, 1, 0. And then the other example that we had was that 2 by 2 for root 5. Was it positive or negative? Oh, root 5? Oh, something about 20 and 5. 4 over root 20. And 2. Negative 2? Root 20. And then 1, root 5, and 2. So these are two examples of orthogonal matrices whose inverse is a transpose. Yeah?
Is there not two of those, since like any from
Oh, it's not the original matrix, it's the transpose of the matrix.
Yeah, but like the one where you have the inverse of that matrix times the matrix equal the enemy matrix. Then would
You mean for P?
Yeah. Well, no.
What?
That's
I mean, yeah, you're right.
Okay. So maybe is it significant? Maybe we should talk about it. No? Later?
The idea of a theorem is like something that when you see, you're like, oh, yeah,
Well, it's not always, yeah, duh. Because it's some of it is so deep that it's yeah. But this one is yeah, duh. Sometimes those theorems where it's yeah, duh, it's like it's more presented as a corollary, which means it follows immediately from a previous theorem. So this one kind of followed immediately. So maybe they should have called this one a corollary. No, see,
math, PhD dissertations.
sometimes. If you can prove one of those big ones. All right. Here's some examples. I don't know if we need to do these examples, because if they are in fact orthogonal, then the inverse is just the transpose, and so that's easy enough to do. Oh, let's do some trig. Why don't we do an example? Oh, really? It's 150 already? So, how would we show that this is all orthogonal? This is all gonna, I don't want to do it, skip it. It's a good exercise for a trig class, because it's a bunch of identities and it's a bunch of pushing identities. So the idea is that if you take this as a vector, we have to do a few things. We have to first dot them to make sure that they're equal to 0. So let's call this V, U, V, and W. So U dot V, let's just do an example. So this is negative cosine squared theta sine theta plus cosine squared theta sine theta plus 0. And somehow you should get this to equal to 0. In this case, it seemed pretty obvious. It worked out. And then you need to do U dot W and V dot W. And you'll see that when you do this, you'll come up with some interesting trig identities that you'll have to use. And then the other thing that you need to do is to make sure that for this matrix to be an orthogonal matrix, we have to also make sure that this has unit length, which means the magnitude of U has to equal to 1. So that would be cosine theta sine theta squared plus cosine squared theta squared plus sine theta squared. And you'll see a bunch of sine squared plus cosine squareds popping out of here, and you'll do some factoring and stuff like that, and you're going to get this to equal to 1. And so likewise, the magnitude of V and the magnitude of W should all equal to 1. So I was kind of looking at it and thinking, oh, this would be a fun trig activity to do, but when I saw the time, we need to move on. All right, a couple more quick theorems. I don't know about quick, but a couple more theorems that find relationships between orthogonal matrices. Or these theorems where, the following are equivalent kind of business is a good way for us to check if something is orthogonal. Maybe there's another way to check if something's orthogonal. So in this case, Q is orthogonal if the magnitude of Q applied to X is equal to the magnitude of X, and if Q applied to X dotted with Q applied to another vector Y is equal to just the dot product. The dot product of those two is equal to the dot product of X and Y. What does that mean?
Orthogonal matrix kind of looks like a scalar.
Kind of, yeah. So Justin just said an orthogonal matrix is kind of like a scalar of 1. Now, formally, our designated 1 is the identity matrix, right? But you can also take a look at another matrix that might not be exactly the identity matrix, but can play the role of 1 when you're applying it to vectors. So you can kind of think about it that way. That's an interesting way to think about it.
So this also has to do with the eigenvector and eigenvalue.
Yes. Well, hopefully it will, right? In the next theorem it does.
Yeah, I kind of think of an
So here are a couple more theorems. If Q is an orthogonal matrix, then its rows form an orthogonal set, orthonormal set as well. So not just the columns, but also the rows form an orthonormal set. And then if Q is an orthogonal matrix, then the inverse is also orthogonal. The determinant is equal to either positive 1 or negative 1. Eigenvalue has to be equal to positive 1 or negative 1. And if you have two of them, then the product, if you have two orthogonal matrices, then its product is also orthogonal. Some of these probably should have been added to theorem 5.6.
Does this orthogonal matrix have to be square?
Not necessarily, but in these theorems they are square.
What about for 5.8? I guess it does, just
Because we're finding determinants and eigenvalues and inverses. Okay? All right. Well, that just means lambda is equal to plus or minus 1. That means all your eigenvalues or eigenvalues are either positive or negative 1. So that's what the absolute value of 1. Okay, that's the first section, and I can just copy and paste the first definition in the next section, but we might as well just do that next time. So next time we need to rush through and get as much done as possible to get to the QR factorization, and we might skip around just to get to the main meat of that idea that we want to take a matrix and be able to factor it to a Q and an R. What's a Q and R stand for? I forgot what Q and R stood for. It's like an LU decomposition, but QR is something to do with how the bases are set up. Anyways, we'll do that next time, and then hopefully by next time I'll have an idea of what your final exam is going to look like and what that's going to include, so I can tell you a little something about it.
Open up to all the homework